So trying to find the angle between two vectors, if we put the two vectors together and put theta in the middle, we'll say suppose theta is the angle between vector A and B. If we were going to put another vector in here to consider the vector between these 2 points here, we would either go, we would go negative B plus A, or we would go negative A plus B. So for this, we're going to say, well, if I'm going to go from here, I'm going to go negative A plus B. So I'm going to go along those vectors. And then I would call this vector B minus A. Okay, so that means we've got three different, we've got a triangle, we've got three different sides. And it's worth considering now, well, realistically, if I wanted to draw the triangle without vectors, realistically what we have here is a triangle here where we had this side here is length of A, this side here is the length of B, and then this side here is the length of the vector, I've done it the wrong way around, B minus A. Okay, so we're using the modulus to show the length here. And so this means that in this form here, and we had theta was between A and B, we can actually use our cosine rule to figure out how big this angle is here. And we don't actually need to, luckily this far side, we know that because it's this value here. So in our example here, all right, we're going to use, what have we got? Now, unfortunately, I've doubled up on a variable. You can see in my example here, A is actually B minus A. We've got B here is the A, and then we've got this other one, C is B. So let's swap those values in so they actually make sense. So we're going to have this first value here will be the modulus of B minus A, and it's going to equal, and that squared is going to equal our B side, which was this side here, is modulus of A. I should have really pre-planned this a bit better. That's squared, plus the C length is B. Okay, and then minus 2, the length of A, length of B, cosine theta. Now, this is going to use a few of our algebraic properties that we've just previously talked about. So this thing here, squared, is actually going to be, if you think about our individual components here, let's just write up our vector. So B is going to equal B1, B2, B3, and A would equal, I'm drawing these very close to each other. Let's do a comma there, A1, A2, A3. This would mean our B minus A vector would be B1 minus A1, B2 minus A2, B3 minus A3. Now, the reason I bring this up is because this first one is saying the modulus squared, which when we look at that, am I going to have enough space to write this out? I should have enough space. Okay, so this is going to be the square root all squared of B1 minus A1 squared plus B2 minus A2 squared plus, I'm going to have to write a bit smaller here, B3 minus A. Okay, we're going to have to slide this out a little bit. Okay, B3 minus A3 squared. Okay, so we've got that all set up there. Let's just stretch this so the notes look a bit better. Okay, and luckily the square root and the squared here, this and this are going to cancel. Okay, so then we're going to have, we've got our A squared. Now, conveniently, we've actually seen this before, and this is going to be the dot product of, should I specify that? No. we don't actually need to. Let's just write it fully out. So this is going to be the square root of a1 squared plus a2 squared plus a3 squared. And then we've got, so that is this term here. We're going to do the same for b. Oh, and this is all squared. And then plus square root b1 squared plus b2 squared plus b3 squared. Okay, and then our final term here left is going to be minus 2ab cosine theta. Oh, we did run out of room. Okay, so next line down here. Now this is all very squishy. Let's actually drag this over here out of the way. So then we can, just going to move that back a little bit. And let's just clean this up. Otherwise it'll look messy if you're looking at the notes. So A, B, arrows on these, cosine theta. Cool. All right, our next line here. So these square and the square root cancels out, and I'm left with b1 minus a1 squared, okay, plus b2 minus a2 squared, plus b3 minus a3 squared. Now this is going to equal a1 squared plus a2 squared plus a3 squared. Okay, so that is the square and the square root have cancelled out here, and we're left with plus b1 squared plus b2 squared plus b3 squared minus 2ab cosine theta. Okay, now I'm not going to bother with this because it's going to take too long, but this thing, when I expand it, is going to be b1 squared plus, take 2a1 b1 plus a1 squared. Now, you should hopefully notice, if I get the yellow here, this b1 squared and a1 squared is going to cancel when I subtract from these values here. Each of these particular ones, let's do that one there, is where they're going to cancel, and then if I use another color, this orange, these are going to cancel with that one, and then this final one here is going to cancel with that and that. So what we're going to be left with is this middle term of each one. So we're going to be left with negative 2a1b1, negative 2a2b2, and negative 2a3b3. And this is all going to equal negative 2ab cosine theta. Now, if I take out all the negatives, if I multiply both sides by negative, I'm going to get rid of the negative 2 and all these negative 2. Everything becomes positive, all right? And then if I factorise out a 2, I'm going to get here, or actually no, let's divide both sides by negative 2. So I'm going to have to slide that up because I did not give us enough room for this. So we'll slide this up, and we're going to have this divided by negative 2 and this divided by negative 2, and you should notice, will cancel, and that will cancel with that. And now we are left with a1b1 plus a2b2 plus a3b3, which we should hopefully notice that this thing here is the dot product of the vector A and B, and it's going to equal the modulus of A times the modulus of B cosine theta. And from this, we can state that cosine theta equals A dot B, so the dot product on the top, of the modulus of A times the modulus of B. So that's the proof. Now, if you don't need that, but this lets us pretty much work out the angle, and now we could take the inverse cosine of this scalar here, or this constant. Okay, so I just wanted to go through that proof because it's a big part. The angle theta between vectors A and B can be found. Now, geometric properties of the scalar product, these are vital. So this means if we get A dot B equals 0, if and only if A and B are perpendicular. So if you look back here, the denominator here is just going to be a length. So if you think about cosine theta only happens when it's only equal to 0 when it's theta equals 90 degrees or negative 90 degrees. So if this angle is 90 degrees, these two dot products equal 0. Now this next thing, if the dot product equals the length, so we're looking at these here, if this equals this, it means that cosine theta equals 1. Now we should know from trig that means the angle theta is 0 or 180 degrees. So in here, this is sort of saying theta equals 0 degrees or 180 degrees, or I'm trying to think of the way to say it, but pretty much we're looking at 0 or 180, all those values that are a certain degree out of that, and this one theta equals 90. Now, next bit here we've got if A dot B equals so this is our formula again. If theta is acute, then our cosine theta is going to be greater than 0. Okay, so we're looking at these two things here, these lengths, they're going to be positive. So if we can just do the cross product and we get a positive value here, it means that theta is between 0 and 90 degrees. Here, if theta is obtuse, we're looking at the dot product here is going to be a negative value. All right, I'm just going to pause for a sec.